in order to provide you with a really wide set of viewpoints, see the width of the panel, on this question of ignition ambition. What are we actually expecting when? What hurdles need to be overcome? If you'd care just briefly to introduce yourselves one by one, because you will do a better job of it than I, starting with you, Ben.
Hey everyone, I'm Valys, co-founder and president of Xcimer Energy. We're pursuing laser inertial fusion based in Denver, Colorado.
So I'm Kim Budell. I'm the director at Lawrence Livermore National Laboratory, a large multi-purpose national security lab in the United States.
Chris Morton, chairman of Tokamak Energy and one of the very early investors.
Brandon Sorbom, chief science officer and one of the co-founders of Commonwealth Fusion Systems.
Francesco Sciortino, co-founder and CEO of Proxima Fusion, based in Germany and spun out of the Max Planck Institute for Plasma Physics.
Chris Mowry, CEO of Type 1 Energy.
Great. Well, thank you all very much. So we had some extensive chats before convening this panel, which unfortunately I wasn't part of because my dear friend Jeff was, and he is unfortunately ill. But having gone through the material, it struck me that I'd like to start off by asking Francesco about the question. You brought up the fact that there are different definitions of ignition, and if we're going to deliver ourselves 40 minutes of this, we might as well get clear what we're talking about.
Fair enough, yes. Between the different, in the zoo of solutions, let's say, that people are tackling in across fusion, ignition means either that the amount of energy from the plasma absorbed by the plasma is the same as the amount of energy that is coming out of the plasma on a physics level, or it can mean that enormously more energy is coming out. The definitions vary between the different fields. Maybe better than focusing on that language that has differed across the field over the years. Maybe better to talk about the net energy on a physics level, on an engineering level, and then on a commercial level. On a commercial level, I mean, we often refer to this as a Q, so the ratio of out versus in. On a physics level, that means really on a plasma physics level. On an engineering level, means electrons from the plug and giving them back to the plug. If you get to Q economics greater than 1, that means you've made money, which of course is kind of important at the end of the day. So that, I think, is the kind of separation that every single concept eventually has to go through.
And it was the first of those Qs that we were talking about earlier, Kim, with NIF, yes?
Yes, I think it's the middle one you described. We're very far from wall plug Q of 1, but we're using, we're well past the threshold of the physics ignition in the capsule and to a target gain, integrated system gain of greater than 2 to 3.
Brandon, I wondered if I come to you for a question of how do you actually compare, how do you standardize the comparisons to know that people are doing what they say they're doing and to compare between different, I mean, sometimes very different technologies?
Yeah, I think that's a great question. And Ross actually showed a plot from, there was a paper published a few years ago by ARPA-E in the US showing triple product. And I think that's a good metric that you can compare all the different zoology of ways of confining a plasma. As you can look at the triple product. And he said, look at all these dots that are on this plot from all the machines that have been built in the past. And I think that's a really good way. I think in a more general sense, it's important for companies to publish just the same way that academia and the public programs do, because that really builds trust in the public. Again, like Ross was saying, you have to go out to the communities that you're building these plants in. And fusion is kind of a weird thing. Not everybody learns about it in school, unfortunately. Hopefully someday in the future that'll change. But you really have to educate people about what's going on. And I think a big part of that is actually publishing your results and being very transparent about what you're doing and having a common metric to compare everything.
So because it's not taught in school and because it's just possible that a few people looked at Ross's fascinating chart and thought, my God, what a lot of lines and colors and blurs. The triple product, what are the three things in it?
Yeah, the triple product is a metric that's been known since sort of the 1950s. Of these are the things that you need in order to achieve fusion. So one of them is you need density of fuel. Then you need the temperature to get the fuel hot enough to fuse, to get the atoms to move close enough together. And then the last thing you need is a little bit more amorphous. It's called confinement time. It's basically how long you can keep all of the energy from leaking out of your plasma so that the energy can contribute to keeping it burning so you can get to an ignition condition.
And can I use that measure to compare inertial fusion as at NIF and magnetically confined fusion as at Commonwealth?
Yeah, in broad strokes, you can definitely use that metric to confine all the different techniques that are trying to get to commercial fusion.
So another thing that you need, of course, is a supply chain. We were hearing about that from Bob. I'm sure we're going to hear about it from a number of people. Chris, tell us a little bit about where you think we are in terms of getting to ignition, in terms of where the supply chain is.
No, it's very interesting. I mean, I've got a background also in biotech, and I'm old enough to have kind of worked from the beginning of the discovery of monoclonal antibodies through to today, where they're ubiquitous as drugs. And I think, Bob mentioned that, CFS is very vertical, and I would say that Tokamak Energy is rather horizontal insofar as we really focus on areas where we've taken prototypes forward, we've built them, we operate them. We're just about to operate the Demo 4, which is the first full Tokamak set of magnets together. And we operate the ST40 spherical Tokamak, which some of your colleagues have visited. So I think a bit like Ian, we see the building of competencies of supply chains, materials, but also very importantly people, as something which is iterative. There's you start that with discovery, with development, R&D, you feed that into industry partners then supply you and run down the learning curve. I think the really important thing for all of us in this room, I'm in no doubt that one of us companies is going to produce break even pretty soon, and that we'll be well on the path to designing and delivering our first prototype delivery machines for electrical power. I think the STEP program, the other programs around the world working in that direction are all part of that collaborative effort. So what's really important is that we work together and develop this large network of suppliers and run down the learning curve, because at the end of the day, it's going to be an economic mission. We need to deliver cheap, baseload, renewable energy, heat, power to decarbonise a world which is becoming much more energy intensive every year as we move forward now. So it really is, I say we're horizontal, but we work with an enormous number of collaborations and we work with private-public partnerships to achieve that.
And when you say coming together to learn, what are the actual institutions or mechanisms by which you do come together for that sort of thing?
They're really quite varied, and it does depend, from country to country. Europeans do things a little bit differently to the Americans. You see the difference between the DOE milestone program and things like STEP in the UK and potentially Japanese programs. So there's no one answer to that, but it's really a question of the philosophy and the culture of organisations, the culture to collaborate, the culture to publish, to be transparent, to share data. I think that, for all of us, the most important thing is that we get there quickly, the planet needs it, and that we get there very efficiently at a low cost. And we only will do that by running down this enormous amount of learning across the supply chain, down the technologies that we need to do. And so, I very much welcome the initiatives that governments are doing, but also private companies, and indeed, events like this today. This is, one of the first events in the UK looking at, from an economic point of view, fusion, where it's taking us. All these things are important.
Kim, we were talking earlier about the next steps for NIF, and what Chris was just saying was reminding me of the question: what are the next things that you need? What are the things that need to be tested? What are the gaps in technology that you can help sort out at this point?
So there are a set of things that are common to all of the approaches that we care about. For example, materials that can survive in high radiation environments over long times. Most of the approaches that we've talked about so far rely on a tritium fuel cycle. So that requires both tritium to fuel the power plants, but then a scheme for a closed loop fuel cycle for the power plant itself so they can operate economically. There's a lot of component technologies, blanket materials, and other things that you need to build out a power plant, and then schemes for how you can operate and maintain a plant over a long period of time. And that, again, depends. Those are a little more divergent between the different approaches, but there's a lot of technology to be done. On the good news front for that first stack that's common to all these approaches, there's a real opportunity for the community and the public and private sector to come together around those. And so there is where I see a lot of the government programs, particularly in the US, focusing on bringing public sector entities in to work on, for example, radiation resistant materials. I have a very large material science department. There's not really any reason for the industry to build up that expertise, but to leverage academic and national lab partners to really solve those technology gaps.
That's an interesting question because it makes me think of something else we were talking about where Livermore actually is. Is there any need for sort of like geographical co-location? It seems to me that you're all based in pretty different places. But if you think about, as Bob was talking about earlier and as you were mentioning, Chris, if you think about biotech boomed coming out of clusters, 128 and South San Francisco and those sorts of things. Fusion doesn't seem to have a geographical heartland like that. Does it need one?
I think there are some advantages to that, and we're seeing that. There are clusters around the country, particularly relationships between specific institutions and clusters of companies. So Commonwealth and MIT is one example, where it grew out of a very rich science and technology ecosystem. That's a great way to launch companies. For us, we're seeing a lot of activity in the California region because of our centrality to the inertial fusion energy industry. Now, that doesn't mean all the companies are locating there, but for certain companies, proximity to the lab is really useful for them. Proximity to our experts, our high-performance computing capabilities, really being able to interact on a real-time basis. So it depends, and I think you'll see, at least in the US, a number of regions positioning themselves to be the fusion center in the country. So again, healthy, building a good ecosystem, but proximity does help for some things.
Other than the Bay and the Boston area, what are the others? What are the other contenders?
So there's facility being built in Colorado, for example. So maybe you'd like to comment on that.
Yeah, I raised my hand because Colorado, especially northern Colorado, between Denver, Fort Collins, and Boulder, has always been a center of optics development and suppliers. And we are seeing, one reason we ended up locating Xcimer in Denver is we are seeing a lot of momentum around that region as a hub for inertial fusion. We actually have Marvel Fusion that's collaborating with Colorado State University, building a facility in Fort Collins.
Did you say Marvel or Marble?
Marvel, or Marvell.
Right.
They're based in Germany. They have a collaboration with CSU, and we found it's a great area of the country for talent and resources.
And where are you based, Francesco?
We started in Munich, where the Max Planck Institute for Plasma Physics has its largest center. But then, speaking of ecosystems, we started working with the Paul Scherrer Institute in Zurich, great place for magnet engineering, and then with the UK Atomic Energy Authority here in Callum. We've heard a lot about the work that UKA has been doing on building up that ecosystem. So in Europe, you could say that there are a few key fusion research centers and technology research centers. KIT is another one in Germany. Eventually, if you want to work as a pan-European company, you have to learn how to leverage these partnerships.
And what about Line 1?
Well, we're actually located in 4 different countries, the US, Canada, the UK, and Australia right now. So maybe this gets back to your original question and comment around ignition. Perhaps we also need to start thinking about another type of ignition. And, Ian reminded us just a little while ago that history is littered with technologies that never got built. So I think one of the things that as we move through the process of trying to commercialize, we need to start thinking about as a concept is ignition from a market adoption perspective. And how do we organize the industry and connect into the broader energy market and energy ecosystem in a way that we can actually scale this technology? If we just build 30 one-off plants, we're not going to move the needle on climate change, on energy security, energy resilience, any of those things. So as we structure our companies and connect into the broader supply chain and value chain, that's really what the global energy market is. We need to think about how to structure this in a way that actually lets us ignite fusion as a major contributor to the future of energy.
And what does that actually look like? Is that something like what other Chris was talking about in terms of making sure that the supply chains are there to serve everyone, or?
Well, I think that's part of it, but I think what we need to think about very closely is the value chain that exists today and how fusion can most efficiently plug into that. Do we really need to reinvent how to build a power plant? I don't think so. There's lots of good energy companies out there that do that for a living today. It's very hard to do that and to do that well. And so, but it also comes back to something about scale, right? And how do you ask about geographical location and should there be these regional centers? But the energy market is global. So how do you structure companies and the relationship to this global market in a way that we can scale? And I think those are really important questions. And those are things that as we emerge from the lab and actually start to build power plants, we need to understand in what way we can actually scale fusion. It needs to be more than just the technology. And so we're fortunate enough to work with an end customer of power generation, TVA. TVA is interested in building a fusion power plant. They have the expertise to build it. They know how to operate a power plant. They know what it means to maintain it. And they can feed back to the technology developer the critical things that are going to make a difference to the end market in whether or not these technologies are ever deployed at scale. And I think we really need to start paying attention to that. And instead of trying to push the ball down the field, almost think about how do you change this thing around in a different orientation where we're being pulled into the end market. That's a really important concept that I think all of us need to start spending time on.
And I think you're implicitly saying that the history of the field has been scientists pushing in a general direction that they think might be useful. And I think we heard something similar from Ian, and that you now need companies that are actively thinking about how to produce the guts of power plants.
Well, I mean, outside of the fusion system, for many of the technologies we're talking about, and those of us in the room who are working on them, the rest of this is already industrialized. It's been industrialized for hundreds of years. Many of the technology concepts that people are pursuing ultimately, make steam to run a turbine and a generator. Turbine generators have been around for hundreds of years, right? So again, should we be reinventing all of that knowledge around how to do those things, how to maintain and operate? And so I think, one of the things we're trying to do at Type 1 Energy is really plug directly into this end market. And that's why we're engaged with companies like TVA, energy company in the US, but not just in the US. We're building an ecosystem of these customers around the world where we're actually talking to them about how does this fit into your energy system, in your portfolio of power generation? Because ultimately, that's what's going to lead to this ignition of market adoption.
Isn't this a terrible time to be building a global enterprise like that?
Well, I would assert that this is absolutely the most important time. If the best way to ensure that your company is fragile is to be located in one place or one country, right? We need to think globally, act globally, and getting back to another concept that Ian talked about earlier, are we going to be leaders or are we going to be followers?
Who's we there?
This industry.
Right. Because we've also heard the idea that fusion is a national priority, that it's a strategic industry. Doesn't that rather argue against a unified global industry?
Well, how many nations are there? Maybe it is a national priority of the UK. It's a national priority of Germany. It's a national priority of the United States. We need to lever the local, provincial desire to have those priorities and think about this globally. There are many countries who want to be the national leaders in fusion, and that's a good thing, right? And we should plug into that. This really shouldn't be a partisan viewpoint of us versus them, but we need to transcend that, and I think there's an opportunity to do this. Certainly, the energy industry works that way. If you look at the big energy companies around the world, the Mitsubishis, the Framatomes, the Siemens, they work globally, right? They're not stuck in one specific country or jurisdiction.
Though the vast majority of all solar panels come from one particular country and jurisdiction.
Well, I think that's an artifact of an industry that's growing and maturing, right? Again, this is a whole process of commercialization where you move from the basic science of this thing to actually building a commercially viable product and a solution that plugs into a global marketplace, right? And that is that we need to move out of that line of thinking, because that's the way the real world works. If we're going to be a part of the real energy system in the world, we need to play that game. We need to be part of that way of thinking.
How does that reflect a European viewpoint, Francesco?
Yeah, I think Chris' point reflects lots of wisdom, let's say, about how energy companies reflect how they look like today. My personal view is there is more and more geopolitics, not on a national basis, but more on geopolitical blocks. So Europe, the US is developing its own fusion champions. I don't think we're looking at a world where the Chinese fusion champions are exactly on the same. There is clearly some geopolitical creation, let's say, that is going on. The supply chain, I think we can all agree, we would like it to be completely free from trade barriers, for example, and we know what's going on there, right? So, for example, now for all the magnetic confinement fusion companies in the US, accessing that supply chain across Europe suddenly is a bit more expensive. Mm-hmm. The reality is, I think we are looking at technology, as was mentioned earlier, that has an aspect of resilience, of independence in the supply chain. All of that, I think, brings us to create some tension. I think we would want the world of energy to be always free from all of this politics. The reality is, I think we need to be prepared for some of that politics because it's not dictated by us.
Yes, the famously political free world of OPEC. Getting energy out of politics and vice versa may be challenging, may even be more challenging than getting the deuterium and tritium to do their thing.
The perspective that we have starting in Germany is, it's a country that has powerful economy, has absolutely destroyed its energy policy over so many years, and it looks a bit like a joke as of today. Germany and Europe really need to get their act together on taking that research that has been spearheaded to a significant extent by European research institutions and actually commercialized. Mm-hmm. The one thing that we don't quite do so much across Europe, and we often leave our US friends to take the lead in that step, I think infusion is one of those cases where the European Union, but the UK, Switzerland, and so on, really need to realize we need some of that supply chain resilience in Europe, and we need our own fusion champions.
Alex, I was wondering, we've sort of like accidentally partitioned into magnetic confinement and inertial confinement over there, and you're at the far end. Does it look the same from the inertial confinement point of view?
In terms of international collaboration? I think there's been a lot of historical interest in inertial fusion across the world, right? There's a large laser facility in France that's similar to NIF. I think I might have a more optimistic view in that I think as different fusion companies reach milestones and demonstrate technical progress, a lot of these other supporting factors will start to come together. I think, so my co-founder and I got involved in inertial fusion in grad school around 2010 because we believed even then that inertial fusion was the most promising approach, the most proven approach. We're very thankful that NIF achieved the result that they did. And that result in December of 2022 brought about a sea change in how people think about fusion. And I think as other companies and other approaches achieve similar milestones, I think a lot of the other factors will start to come together around supply chain, right, around government support and government collaboration. If you look at what the U.S. is trying to do in the Department of Energy's milestone program, right? That was modeled on the NASA Commercial Crew, commercial space programs that initially got the commercial space industry off the ground 15 years ago. And I think we're getting to the point where policymakers, lawmakers are going to see fusion in those terms and see it as a priority to support in the same way that they did commercial space.
I'm intrigued when you say that I can't straight back to Kim, but when you say that you got interested in grad school, were you interested because you were guys who were really interested in lasers and wanted to do something with them, or were you interested in fusion and lasers were just a tool to you?
Well, all these technologies are super cool, and one of the great things about fusion is the opportunity to work on so many interesting problems that have the potential for such a significant effect on humanity. But I think for me anyway, it was about energy and just about the potential for what you could do, what humanity could do with an unlimited, clean, safe, reliable, abundant source of energy. Renewables are great. Right, and I think certainly, as we've maybe discussed this morning, there's a path to replace humanity's existing energy consumption with renewables at reasonable cost. But if you look at the history of the Industrial Revolution, right, and what happened from 1800 until the 1970s, air conditioning, the Concorde, supersonic travel, all of that came from an increasing abundance of energy. And I think fusion is the only technology that gives us a path to get back on that trajectory of using more energy for good. So that's what got me involved, or got me interested. And inertial fusion, has a long history of work at the national labs and other organizations. And so even back then, my co-founder and I viewed it as an engineering problem. And so what we ended up doing at Xcimer is focusing on how to reduce the cost of the laser that you need to achieve this result. And I can talk more about that if you like, but.
No, but I'm interested. And also, talking of the energy transition reminds me to plug, I think, one of the books of the year from last year, which was a book called More and More and More by Jean-Baptiste Trezoz, which is a fascinating retelling not only of how humankind got more energy, but also how we started thinking about the idea of there being energy transitions, and also crucially, and I think very importantly for the debate here, the fact that almost all new forms of energy end up being additions as much or more than they end up being substitutions. And that it seems to me that there's a thinking about the energy transition that we're now undergoing, that there will be one thing that will take over. And I think one of the things we see, it's not even clear that there's going to be one form of fusion energy that takes the biscuit. But Kim, you were trying to come in on something, and I rudely talked across you.
Two things. I don't want to get into the shouting match, magnetic versus inertial. We work in both. We have long history in both approaches. I think it's really important, and both fields have seen significant advances in both the fundamental science and the technology that's required to take them forward. I will note on the triple product plot, the only approach and the only facility that's ever gotten to these ignition conditions is the National Ignition Facility with inertial fusion. So there is still science in this that needs to be demonstrated, and my fingers are crossed that many of these approaches we're taking are going to be very successful in the coming years. On the inertial fusion front, parts of the supply chain for inertial fusion and parts of the science base for this have been very international for a very long time. Laser technology is very distributed internationally. So again, many approaches trying to improve the efficiency of laser systems and drive the cost down and build supply chains for critical components like diodes, which are one of the key technologies for many of these approaches. So there's a good foundation building there that allows you to have both a national and an international approach. And I think this idea of thinking about this in both of those contexts is important. There are always going to be national sovereignty questions around energy technology, particularly ones that can scale the way fusion can scale. But having multiple approaches and multiple different countries pursuing different approaches and collaborating where possible and differentiating where necessary is really going to be a key to success for this industry.
Brandon, you look like you wanted to make a point there.
Yeah, I think it's, so like Bob, I'm also a really big fan of the history of technology, and I think it's really appropriate that, we're here in the UK right now. There's a great example in fusion itself that happened in the 60s of international collaboration, where when in magnetic confinement, this device called the Tokamak that we're working on, there was a device, the first one of these was built in Russia, and they got these really amazing results, and nobody believed them at the time. And actually, there was a team from the program in the UK of people who were experts at measuring plasmas that was actually allowed in 1969, at the height of the Cold War, to actually travel to Moscow with boxes of lasers, because actually the diagnostic that was being used was a laser-based system. And so you can imagine that it sounds kind of crazy that, people from
sounds like the great James Bond film that never
ends. Yeah, right? But this team went over and actually verified the results of this Russian Tokamak. And I think that was a really great example of how this, there's a history already in fusion of international collaboration. ITER, when ITER was established, it was with Reagan and Gorbachev. that did a lot of the the founding work of setting ITER in motion. And so I think there is really this long and rich history of global collaboration in fusion. And I'm really optimistic that things always go up and down, but I'm optimistic that looking at that history that collaboration will continue.
I think working in fusion must select for optimism. I'm going to come back to it later, actually, but we have some minutes for questions from the hall. I can't tell you, stretching, sir, or... No, you're just leaning. Yes.
Christina Yan Zhang from the Metaverse Institute. So we all know fundings for nuclear fusion can be a major challenge in the years ahead. So if there is a magic figures you think can really help to commercialize nuclear fusion at scale to help us to fight climate change, how much money do you think the industry will need in the next 10 years? Thank you.
Great question, because not least because it makes you actually give numbers as an answer. How much investment does the industry need over the next 10 years, given we're in the context of ignition ambition?
I think it depends what the actual ambition is, right? And how you try to go about accomplishing this. So I want to just...
You're an ambitious guy, Chris, so why don't you, max out the ambition?
Is the ambition to kind of create a completely separate integrated capability to generate electricity, or is the ambition to get fusion electrons on the grid as quickly as possible? Because I think the answer to your question depends a lot, again, on how we integrate into the global energy system. And I also think that we need to understand that there's a whole spectrum of technologies. Many of them have very, very powerful value propositions, but there's also a spectrum of technology maturity. And I think one of the things that has to happen in the industry is that we need to actually build some fusion power plants. We need to create a belief that this is actually happening, right? And they will be many, many technologies that will continue to evolve and get better. But I think as an industry, we need to get to the first rung of the ladder. And what does that take? That's not $100 billion. I also think it's unrealistic. We need to create a solvable problem for us. So in the last, I think the running total for the amount of private capital invested in fusion is something like 7.7 billion or something like that over the last, since the beginning of time, something like that.
Well, certainly since the Fusion Industry Association started making its graphics, yes.
So let's pick 10 years or something like that. So the idea that I think that number is going to be orders of or multiples of that in the next 10 years from private capital, it's possible, but I think it's unlikely. So I think we need to turn the question back around: is how do you solve this when capital is actually a limitation, like every other resource here? And I think we need to plot a trajectory for the industry to build power plants in an environment, a reality-based environment where there's not going to be unlimited funding. And I think we need to get these first-generation plants built with the recognition that there's limited funding. And again, I think that means that we need to pick trajectories that make maximum use of things that already exist, because that means the things that have been developed, we need to get that first generation of plants out there in a way that the financial markets can actually support.
Okay. I take that point. Does anyone else want to say, the number that they would ask the fairy for? Okay, there were some fairy askers down there. Chris first.
Money's just a way of making choices. And I think, to put a quanta on this, if you look at the cost of 2 fighter jet programs, that probably is enough. Or if you look at the cost of 5 new offshore oil fields, that's probably enough. Or if you look at the cost of 50 new advanced targeted cancer drugs, it's all about 25 to $50 billion.
You're getting your fighter jets quite cheaply by modern.
Yeah, no, well, exactly. Exactly. I mean, it could be more, but, do we want 2 more fighter jet programs, or do we want a clean, renewable, vast source of energy for the world. And I think one of the things we, as mainly engineers and scientists, have not done, and somebody asked a very good question earlier, which was, you haven't talked about how we communicate to the public. And I think part of the mess we live in now is because we, as engineers and scientists, have delivered a vast amount of very valuable, life-improving technologies into the world without communicating that, without helping people learn how to use them. And the result of that is people, the world's fragmented into little groups of people who are a little bit frightened about what's coming next. So I think it behoves us to really step up to the plate and communicate that this is about choices. This is about our children and our grandchildren living in a world of great wealth in the terms of the quality of life and duration of life, delivered primarily through things like information technology and fusion power. And we do a lousy job of communicating this, and to some extent, I think that's why we're in the mess we're in.
Kim.
So I would look at it from a different lens. So if you think about the technology gaps that I articulated at the beginning of this, if you want the programs to close those gaps to match the pace of the commercial industry, you need an infusion of about $10 billion, because these are very hard problems, and we need to swarm people to working on them right now. And so we're on a path to work through these issues on materials or tritium fuel cycles or whatever, but we're not moving at the speed that the industry is going to need them. So that would be my answer. Let's make the public programs match that pace so that we intersect the commercial track at the right time to keep this industry moving forward at pace.
You also had your hand up, Alex.
Yeah, I think, for me, I'm not super worried about capital in the long term because, as was said, right, there are large industrial programs, right, that cost $50 billion to build, a new floating oil refinery, right, in Australia, for instance. The major issue is risk, right? I mean, investors need, the market is huge, right? As Bob Mumgaard said, energy is, probably the biggest market there is. There's room for multiple players in the field. And so once investors get to the point that they see fusion as having a path, a defined, confident path to actually play in that market, I think the capital will be there. And I think all of us as fusion companies needs to stay, laser focused on how do we structure our milestones and structure demonstrations and accomplishments to increase the level of confidence that the world has in this technology. And I think if we can do that, the capital will be there.
Francesco,
I would maybe add to that with a view on how it could develop over the years. And I see Matt Revisek here in the front, and he was running me through some hypotheses, let's say, about how the fusion industry may develop. Let's say there are of the order of 10 companies that build technology demonstrators like an Xcimer laser, an HTS coil at scale, 10 maybe on the generous side in reality. Let's say each of those demonstrators are of the order of 100 million. To build a net energy device, it's more of the order of $1 billion. Obviously, as Chris was saying, we don't have infinite resources to go improve our technology. Once we access the market, it's going to be different because we show real value. But I would expect that there are a couple of US fusion champions, a couple European, a couple Asian. And then the companies that actually go and build the first-of-a-kind fusion power plants in the 2030s, those will be projects that should be expected to be 3 billion and upwards, let's say. If you look at all of that, you make some math and you make some estimates here and there, you get to a 50 billion kind of scale, which I think is what we should expect, and we should reflect on. That is the scale of what is needed. Part of it is for the national labs to keep up and to keep helping us, because we're basically fed to a significant extent by the technology that comes from national labs. If we don't understand that order of magnitude, we are going to be handicapped sooner or later.
Right. We're almost out of time, so I wanted to come back. Someone mentioned ITER earlier, and we're talking about large amounts of money, so it naturally comes to mind. How many other devices do you think will have achieved ignition before ITER does? You don't have to say which devices, but that's just a number I'd be interested from the panel. I'm willing to name names, but if you want to come forward. Right.
For it. I think there will definitely be a few, and I think that really reflects how, this infusion of money recently, like you mentioned, the FIA is tracking things, and I think the absolute value is important, but also the trajectory. If you sort of plot the amount of money that's gone into the industry, you can see that it's on an upwards trend, which is really encouraging. And I think putting that money, having private companies partner with the public sector and putting this money into private companies that can move really, really fast, I think does give you a few shots on goal. And I personally think there's going to be a few concepts that make it to ignition.
If you qualified by saying ignition putting electrons on the grid, I would say maybe 2 or 3.
Okay.
May I also add to that? I agree with the general numbers. ITER, we should think about it as a project that has also developed a supply chain. The reason why we're able to actually go so fast is because ITER has actually sponsored that supply chain. So it shouldn't be seen as that leapfrog that we're seeing is all that surprising, let's say. So we're all building on that.
It has taken 3 times the figure that Chris just gave for private capital in the recent era. Okay, well, we appear to be out of time, which is probably my fault. But thank you very much indeed. Please enjoy the rest of the day. I'm sure you will be happy to talk to the various people who will throng to talk to you in the networking session, which is not yet. There's still 2 more things to go before then. But thank you very much indeed. That's a fascinating conversation.
Thanks, Chris.